talked about this, pattern recognition, and then mock interviews. IK provides as part of the program, they provide a certain number of mock interviews, and these are conducted by people who also conduct real interviews in their companies. Now, as we all know, in a real interview, it's frustrating because nobody gives you feedback. They're not allowed to. So oftentimes people are wondering, hey, I thought I did well, but I'm not hearing back anything. And I wonder what I need to, tell me something so that I know what to improve. If a person doesn't know what they need to improve, then it's hard to improve, right? So the mock interviews are what you want to do, and they're a very important part of any program, really, because at the end of that session, you get direct feedback on what you did right and what you should, maybe do differently. And so it's like you can't learn to drive by listening to somebody talk about it. You got to go and do it yourself and get feedback, right? So something like that. And then of course, coding has to be good. That's like like I said earlier, it's a minimum bar. You need to be able to code up the solution, and it should be reasonably clean. It doesn't need to be perfect. Don't waste time on trying to make it object oriented, unless it's an object oriented programming interview, right? Then that's a different thing. But your focus, of course, is on completing it, getting it, hopefully getting the right answer. It may not be the most beautiful code, but everybody knows that you're working in a very, very tightly timed environment, right? We talked about this. Don't say you're done without having actually tested your code. So whether it's a dry run or actually running it, again, depends on the company, right? And yeah, clarity, correctness. I mean, communicate your thoughts clearly. Hopefully your code is not too messy, right? I mean, it has to be readable. Again, it may not be the fastest or the most optimal, but it has to get the job done. Okay. All right. Let's see. Hey Rohan, I don't see a chat. I'm wondering if
Chat is enabled for everybody.
okay, yeah, I see it now. I was just wondering if anybody had any questions and I was missing them.
Sure.
All right, sounds good. Thanks, Ron. Cool. So this is like a list of common DSA. This is not an exhaustive list, by the way, but it's a list of common patterns and topics that get asked in most interviews, right? Because one of the tricks of preparing for interviews, like nobody has infinite time and infinite capacity, right? So you can't just say, okay, I'm just going to go do everything out there in the DSA topics. You do want to prioritize based on what gets asked frequently, and so these are what's listed here as some of the common topics. Today we are going to talk about the line sweep, but let's go there now. All right, so the line sweep pattern, as you kind of the name suggests, it is a way where you think of an imaginary line, and we'll look at an example and kind of talk more about it. But you think of an imaginary line that's going to sweep through the input space, the problem space, and as it sweeps through, as it moves across the input data, it's going to come across certain events that could be, like the start of a range, end of a range. It could be a time range, so start time, end time, and such. So it's going to come across those, and it's going to do some processing. What that processing, of course, depends on the problem that you're trying to solve. But at a general level, it is an imaginary line moving through the input space and encountering the start times, end times, or start of the range or end of the range, and then processing them and making some computations. Okay. So if it's an interval that we are talking about, typically represented by a start and end of that interval, right? Like maybe the start time and the end time, for example, if it's a time interval. And so that's what we basically mean by the line sweep pattern. And so then the thing is, once you understand this pattern, and you solve a few problems related to that, then in the future, if you get a problem that maps to this, it's obviously going to help you figure out your initial thoughts on, okay, I think this is a line sweep pattern, so this is what I need to do, something similar to what you've done in the other problems, right? That's kind of the whole idea. All right. So now what I'm going to do is we'll solve a problem first, and then we will revisit this line sweep pattern. Okay. So the first problem we are going to look at is a meeting rooms problem, which some of you may have seen. But in this, what we are given is an array of meeting time intervals. Okay. So it's a tuple of start time and an end time, and we have an array of those. We need to determine if one person can attend all the meetings. So as an example, well, let's look at this example. So this is the, we have three intervals here, 1, 2, and 3. Okay. So the first one goes from 0 to 30. And then the second one goes from 5 to 10. So let's say, from 5 to 10, something like this. Okay. And the third is going from 15 to 20. 15 to 20. Let's make this a little bigger. Okay. Sorry. Let's do this. So now, if a meeting starts at this point, this first meeting starts here and ends here. But then there's these meetings that are starting. This meeting, for example, started before the first meeting ended. And so you can imagine here, one person cannot attend all meetings. There's a conflict. So we return false. Can one person attend all these meetings? No, false. If you look at the second example, it's from 7 to 10 is one meeting. Okay. The other one is from 2 to 4. So that would be something like this, from 2 to 4. So in this case, there is no overlap. So we return true. That's basically what this is asking you to do. Write code such that if you give your input is this, an array of time intervals, and a time interval is defined by a start and an end, right? So this is one interval, this is one interval, this is another one, this is another one. So you're given an array of those and figure out if one person can attend all the meetings. So if you think of this problem, there's a brute force way to do it, right? And the brute force way would be like you would take one interval. Let's actually go back here. So you would take one interval. Let's say, we take this one, and then we say, I'm going to compare it against all the remaining intervals and see if there's an overlap. Because basically, this is an interval overlap problem, right? If any of the intervals have an overlap, the answer is false. There's a conflict of meeting times. If there is no overlap, for example, in this one, then everything is good. One person can attend, so we return true. So it's essentially an interval overlap problem. And so the brute force way would be you pick, let's say, the first interval, and you compare it against all the remaining intervals. If there's no overlap, then you take the next interval in the input and compare it against all the remaining intervals, right? So you can see how this is like a brute force way to do it. The moment in this whole process of doing the comparisons, the moment you find an interval has an overlap with another one, you just simply return false there. You don't have to continue and check the other intervals because you already found a conflict, so you can return early. Yeah. So that's kind of the brute force way to do it. And so this is basically what it looks like. You take the first time interval and you compare against all the remaining intervals. If you found an overlap, you just simply return false. If no overlap, then you take the next interval and, just basically in a loop, you compare it against all the remaining intervals and kind of like that, right? And so that would be like a brute force way to solve it. So if you were to write the code for that, so you would go, assume that your input is given in, is the and the array of intervals, right? So we would say for I assigned 1 to say input dot size -1. Basically, I'm starting from the first index, not the 0th index, from index 1 all the way till the end. And now I want to compare this, say, with the previous interval. So if I'm going to say if has overlap, okay, and I'm going to give it the 2 intervals. So input I -1, comma, input I. Okay, so if these 2 intervals have an overlap, that means, I already found a conflict. So I'm going to return false. Else, we will continue. We're not going to return true, right? Else we would just continue. So I'm going to remove. So we don't, basically, which means we don't read an else, right? Because it's just going to go back into the for loop. And if you come out, 1 second. If you come out of this, then we would say return true, meaning we never found an overlap and we compared everything. And so in this case, we would just return true. Okay. So let me go here and I want to do one more thing here. Actually, I was already thinking of the optimal way to do it. So this is what I wanted to do here. So we take one interval here. Let me actually add a slide here that makes it cleaner, so I don't have to erase anything. So basically, this is where I want to get to is we are comparing, we're doing an n-square comparison, right? So for each, I'm just going to write it in pseudocode here for now. For each interval, say I1 in the input. So we take one, and then we want to compare it against each of the remaining intervals. So we'll say for each interval, I2 in the input. Okay. Make sure, we'll add a check here that I1 is not equal to I2. Then we say if has overlap. I1, comma, I2. If there's an overlap, we return false. If there's no overlap, then we would come out and return true. Now, I'm going to put it in a different color here. We do want to check here that as long as I1 and I2 are not the same. Let me move it a little bit. Are not the same interval. Okay. So if there's an overlap, then we return false. Otherwise, we just say return true. Okay. Now let's look at the time complexity for this. They are both going to run, both of these loops will run n times, right? This has overlap is essentially just checking, given 2 time intervals, do they overlap? So that is going to be a constant time check, like, O of 1, right? Because you're just comparing the 2 times, basically. And so this is O of 1. Check, and overall, because you have this nested for loop, it's n square time. The space complexity, we're not using any additional space, so it's constant space, right? Now, so that's the brute force way to solve it, where essentially you're taking every interval and then comparing it against every other interval. Now let's look at this diagram where it's basically repeating what I said earlier, but I want to show this recurrence relationship here now. So when we are processing, let's say this interval, right, in this for loop, when we say for each interval in the input, let's say we look at first this interval, we are comparing it against all the remaining ones, right? All of these guys. And then if there is no overlap, if there is an overlap, then we will return false. But if there's no overlap, then we go out in this for loop, and then we look at this interval, right? And then we compare it against the remaining intervals, and so on. So if you look at the recurrence relationship, the time taken to solve it for n elements in the input, n intervals in the input, is some constant c times n minus 1, right? Because when we started here, we had to do these n minus 1 comparisons. So essentially that's what this is. But then you apply some constant c to it. And so that plus whatever time then it takes to do this check for the remaining n minus 1 elements, right? Because when we run this for the out of for loop, we pick one element, we pick this one, then we run this check, which is all of this, and then we pick the next element in the for loop, and now we have to deal with n minus 2 checks, right? Because you pick this, then this is what's remaining. And that's what this recurrence relationship is saying, is time taken for n elements is whatever time it takes for n minus 1 comparisons, so some constant c times that, plus then solve it for the remaining n minus 1 elements. So this is going to give you an n square runtime. Another simple way to look at it is this is O of n, this is O of n, and then this check is constant time, right? So it's n square. So that would be the brute force way to do it. Now, we can do better than that if we use the transform and conquer approach. So we basically would transform the input data, and now once we transform the data, we don't have to do so many comparisons, because let me go back here real quick. So in this case, you see it was n squared, because when you pick an interval here, you got to compare it against every other interval, except of course itself, right? You don't want to compare it with itself. But that's kind of the general high level pattern here, right? And that's going to be expensive. But we can improve on that by sorting the intervals on the start time. So if we do the sorting, then it is the number of comparisons that we would need to do would be much less. And so that would make a huge difference. Okay. And so essentially what we would do is, let's say we sort, this is a new step that we are now adding it wasn't there in the brute force, right? So once we sort the intervals, then what we can do is we can actually start comparing the intervals only against, like we start from, say, the index 1, and we just keep comparing it with only the previous one, because this is all sorted. I don't need to, like, let me go back here real quick. So here, when I pick an interval T1, I need to compare it with every other interval except, of course, itself, right? Because the data is not sorted. The interval with which there could be an overlap could be anywhere in this input. So I need to go have this nested for loop. But now that I've sorted it, I don't need the nested for loop, because I've sorted the data based on the start times. And I'm now going to say for the first index, meaning the second interval, index 0 is the first one, right? So at index 1, I can say, start my loop and say, if there's an overlap between the previous and this interval, then return false. I don't need, so when I take this interval, this one or this one, right? I only need to compare this against the previous one and not every other thing in the input, because of this initial sorting that I did. So of course, sorting costs some time, right? But as you can see, let's say this costs me n log n time. This is going to be O of n, right? It's just one loop. And this is a constant time check that has overlap. And so now from n square, we came down to n log n. Or, if you want to be more precise, it's n log n plus O of n, but that's basically n log n, right? The higher order term is going to prevail. So our time complexity would improve a lot, n square from n square to n log n. The space complexity would be whatever the sort algorithm uses, because this loop here, this code here, uses constant space, right? So any space usage is coming from the sort. If you're using merge sort, well, I mean, that's linear space, right? O of n. If you use quick sort, that's recursion, so it's log n, which is very, very efficient from a space perspective. The has overlap function is, like I said, it's an O of 1 comparison, because it's just comparing the start times. It's taking these two intervals. So let's say, this is my earlier start and the later start, right? Because that's what we did. We are passing in intervals index -1, the previous interval, earlier start time, and then this current one index, right? So earlier start and then a later start. And all we have to do is we have to say, let's say this is my earlier start, and let's say this is my later start. Let's look at what this problem is asking us to do. We are again given a bunch of intervals, time intervals, same thing, start and end. And we have to return the minimum number of rooms that are needed. So this is our input, for example, and then the output says 2, because in this case, we need 2 rooms. So if we look at this, for example, this is my input. So this is the first meeting, the green, yellow, and the blue, and the screen just kind of moved for some reason. Oh, okay, sorry. Okay, should be back now. So these are the 3 intervals, and as you can see, in this, when this is the first meeting, so that requires a room, and as we go to the right in time, this is time here, right? As we go to the right, this meeting starts. So we need 1 room for this, and then we need the second room for this meeting. And then as we go to the right, when we come here, the previous yellow meeting has already ended. So this one can use the second room. So here the output is 2, because that's how many rooms we need, the minimum number of rooms we need to solve this, right? To have these meetings. So that's the essence of this problem, of the problem. And now if you, let's look at how we would apply the pattern, the line sweep pattern here. So here's my sweep line, and it starts here, and then the very first event is the start of this meeting, which is, this first one, the green. And as we go to the right, it will keep encountering these time events, right? So when I get to this, there's another time event. And so what we have seen so far, as we've gotten to that yellow one, we've occupied 2 rooms, right? But now when we move this line to the right, when we come here, we are coming to the start of this third meeting, which is this one. Okay. If we look back to check, has the previous meeting already ended, right? And it has ended here. The reason we need to look back here is because, so when I'm here, I need to figure out how many rooms do I need. I wonder if my screen is too small, because on my laptop I see it. Okay, that should be better. So when I'm here, I need to look back and see, hey, do I need to have a new room, or has the previous meeting already ended? And in which case, I don't need yet another room. In this example, the previous meeting sure has ended, right? Now, there could be a scenario where we have to look back at multiple previous meetings, not just the one of them, but could be multiple such checks that we might have to do. So let's look at that scenario. So let's say while we are processing, we've reached this blue line. So my sweep line, which started in the beginning, has finally come here, and it's looking at the start time of this blue meeting. It's looking at the start time of the blue meeting, okay? Now I need to do the check, and I'll look back to the yellow meeting and see, has that ended? In this case, it hasn't. But then I might have to then also look at the pink one, right? So we look back to the pink now. So we looked at the yellow already. Now we look back to the pink and say that one hasn't ended, and then the red, and then and so on, right? So in the worst case, you may end up checking all the meetings, or a lot of the meetings. And in general, then you can say that to process this point, I, in the worst case, might have to check a lot of meetings or all the meetings in the, and then that's going to be O of n time just for this processing this one thing. And of course, that's pretty expensive, right? Just for one, we had to spend that much time. So what we can then do is we could use a min heap. And a min heap, as you know, is a data structure where the root, you add, let's say you add a bunch of numbers, and the root of the min heap is the smallest number of all the numbers that you added into the heap. Okay, a max heap would be the opposite. It would be the biggest number, but here we are going to talk about just a min heap. So we could use this auxiliary data structure, the min heap, and what we would do is we would add all the n times of the meetings. How that is going to help is, now let's look at the scenario again. When we are looking at this blue, the start time of the blue meeting, right? What we had said earlier was, I need to keep checking for all the previous meetings and see if they have ended. But now, if I have this auxiliary data structure, the min heap, which contains the n times of all the meetings so far, then all I need to do is, when I'm here at this time, I need to check the heap and say, what's at the top of the heap, the root. The root of the heap is going to be the smallest number. It's a min heap. It's going to be the smallest number, right? And that's going to give me the earliest end time. And then I can compare that, and I can say if the root of this min heap is greater than this blue line start time, is greater than this time, that means none of the meetings have ended yet, right? Because again, the root of the min heap is the smallest number, meaning the smallest, the earliest end time. And if even that hasn't, if that's greater than this time, that means nothing must have ended yet, because this is the earliest end time, and even that is beyond this time, right? That's what we are saying here. If this condition is true, but if this condition is false, we will pop that end time from the heap, meaning we'll say, okay, so this end time is less than the start time, so this meeting has already ended. Let's remove it from the main heap. And so by adding this extra data structure, the min heap, we are preventing to have to check everything in the worst case, which is what we were seeing here when we don't use the min heap. Okay, so let's, in the interest of time, let's just keep moving forward. I guess I'm just going to go here. So then our code will look, using the min heap, will look like the following. This is the set of, the input intervals. We will sort the intervals based on the start time. Okay, so we've sorted them. Now what we're going to do is we will use this auxiliary data structure, the min heap, and we push the end time into the min heap. The sorting that we are doing is based on the start times. Okay, now when we use the min heap, we are going to add, let's say, the first interval's end time into it, into the min heap. Okay, then we run a loop and we say, for each interval that I'm going to look at, if its start time is greater than, later, let's say, if the start time is later than the root in the min heap. What is and the root of the min heap? So far, when we've just started, this is the only thing we've added, right? So the root of the min heap is the end time of the first meeting, right? That's what we have added here. And so what we're saying is, hey, I'm looking at this interval and we are starting from index 1. So we are not starting from index 0, right? So if the start time of this meeting is after the end time, then we just get rid of that from the, because that meeting has ended. So we'll pop it from the root, remove it from the min heap. And this check is going to be greater than equal to, not just greater than, because of course, if the times are the same, so if my first meeting ends at time 10 and the second meeting starts at time 10, we don't need a different room, right? So this condition is not just greater than, but it's greater than equal to would be the right condition here. And so we run this in a while loop. While the top of the heap, the root of the heap is, before the start time. So start time is greater than equal to the root. I'll keep popping the root. Okay. Then that means now I don't have to go back to all the prior meetings and do the comparison. This min heap is helping me to not have to do that. And once this loop comes out, that means either the heap is empty, or we have encountered a root where the start time is not greater than the root, meaning that meeting hasn't ended. Okay, so the end time of that is still in the is still in the future, is beyond the start time. So then we come out of the while loop, and at this point we add this current end time into the min heap, and we take this, we initialize this here. I mean, reinitial, or reevaluate this value here, which is the max value of number of parallel meetings or the size of the heap. Now, number of parallel meetings, of course, we initialize to 1 over here, right? And so we are basically just keeping track of the max ever that we have. The number of entries in the min heap is going to tell you how many concurrent meetings are happening. And so essentially at this step, we are just taking what is the biggest size that the min heap ever got to. And that would be what the number of rooms that you would need. There's a question saying, is it possible to just return the size of the min heap instead and eliminate the local variable? The thing is, if the size of the heap changes, right? Because we have this pop root here. For example, let me see if so let's say this is one interval, and let's say this is another interval. So when we are here, we need one room. When we come to this, we need two rooms. And then let's say we have this. So then here we need three rooms. But then this is, at this point, the size of the min heap is going to be 3, right? But then as the meetings get over, let's say I have another one here. At this point, the size of the heap is going to be 2. So if I only look at the final size of the heap, that's not going to give me the max that it ever got to, right? And that's why we just need to keep track of the biggest number there in terms of how many overlapping meetings we have. And that's going to give you the number of rooms needed. So, so this helps us to not, have to do the brute force approach earlier. Now here, we pay the cost for sorting, and then this pop is log n, right? But then it's running inside a for loop. So this for loop would run n times. Every operation that's being done inside the loop is either a pop or a push, and these are log times. This, of course, is constant time, right? So this is the approach that we could use using a min heap. Now there is an alternative way that we will look at in a second here. So I kind of mentioned here the time and the space for this approach. The time is coming, the n log n is coming because of sorting, and then the space, worst case, well, space depends on two things, depends on what sorting algorithm you picked, and then also we have the min heap here, right? So in the worst case, you could say that that's going to be O of n for the min heap also. Okay. Now let's look at an alternative way of solving this problem. And in this alternative way, we won't use a heap. Earlier, the previous one we used a min heap, but now we won't. And this is also a pretty simple approach. What we're going to do here is, so what do we have in the input? We have a bunch of start and end time intervals, right? We have a bunch of intervals defined by start time and end time. What we're going to do is we are going to associate the start time with the value 1, the number 1, and the end time with the number -1. And then we are going to sweep through this interval and add the values. Let me show you here. So here's the intervals, and I've color coded them, so it's hopefully you can see the colors on your end, and hopefully that helps. So this is, you see, this is the, let me pick up maybe a black color. So here's a start time and end time of the green. So the start time is 1, end time is associated with -1. Start time of the yellow interval, end time of the yellow interval. Start time of the blue interval, end time of the blue interval. But you see now here, I'm also showing this scenario where it so happens that the end time of one of the intervals is the same as the start time of another interval. Okay. And so this is what I'm saying here. We have two time events that are the same, the yellow end time and the blue start time. In this case, when we sort the input, and I'll come to that in a second on the next slide, but when we sort the input, we want the end time to come before in the sorted order, in the case where the times are similar, are the same. Okay. Just hang on to that thought, and I'll come back to this slide here in a second. So what we are going to do is, again, we are looking at this alternative implementation where we are not going to use a heap. So we will say for each interval, I want to associate 1 with the start time and -1 with the end time. Okay. So I'm going to use a time, let's say a time events or whatever you want to call it. It's an array. And for each interval, I append into this array the start time and the end time, and this tuple basically, start time and 1 and end time and -1. So that's what my array, this time events array is going to contain. All right. Once I've done this for all the intervals, then I'm going to sort them. Now, this is what I was saying was we are going to sort it on the time, right? We have these times in here, right? Every one interval has 2 entries in there in this time events, the start time and the end time. Start time is tuple, that this tuple contains 1 and end time contains -1. It is paired up with -1. So we're going to sort it on time. And if 2 times are the same, then the tuple with -1, meaning the one that represents the end time, is going to come before the start tuple, right? So let me go back here now. This. So here you see the tuple, the yellow tuple will have these 2 times, and the start time will have a 1 there, and then end time will have a -1, right? The blue start time will have a 1, but this blue start time and this end time are the same, which is 10, right? This and this, same time. So when we are sorting on time, there are 2 10s in there, and we want the 10 that is associated with the end time to come before. So that means the one that's associated with the -1. Okay, and that's what this sort is going to do. Now, when we are done the sorting, we are going to simply, you look at this step is basically trivial now. We are going to ignore this for a second. So we sorted it, and then we just run a for loop over this time events, this array, and we simply add the value of each of those tuples. Now the value is either 1 or -1, right? And you can imagine the very first thing is going to be, when you're starting the very first meeting, it's going to be 1. And then once we do that, we add it here, and then we have this max numpattle meetings, which we initialized up here. And we say that's the max of, basically just keeping track of what the max value of that is, max of max num meetings or the current, this value. basically. And as you sweep through this time events, which is what this for loop is doing, you're adding the value. So you're going to add 1. So let's say there's a, I'm going to draw here. Actually, maybe it's better if I have this diagram here. So maybe this is better to look at. Let me pick a color. Let's say red. So when I start here, the first thing I'm going to look at is 1. So we will add 1 to it, right? And then the next thing we will look at is 1 again. So we'll add 1 to that. So now the value is 2. The max value that we have seen is 2. And then what are we going to see? We're going to see there's going to be this and this, but we wanted the end time to come first, right? So we will see a -1. So 2 minus 1 is 1 now, and then plus this one is again 2. So you see, and that makes sense because here we need 1 room. Then we come to the yellow meeting, we need a 2nd room. When we come to the blue meeting, we don't need a 3rd room, right? Because this yellow meeting has already ended. So this is still the 2nd room. And that's why you see when we added this one plus this one, 2, and then the -1, so back to 1, plus 1, 2 again, right? So that's basically what's happening. We are simply adding the ones and the -1s. So that's what this loop is doing. It's just simply adding that and keeping track of the max, and we return the max. So this is another way to solve this problem. And in this case, we didn't use like a heap or anything, but we just associate this, the n times and with 1 and -1. And if you look at the time for this, well, this is O of n, it's just iterating over that. This is, let's say, n log n for time. And then this is just running over all the events. So O of n, what's happening inside this for loop, they're all constant time operations, right? So the complexity of this piece of code is O of n, this is n log n, and this is O of n. So overall time is n log n. And space is, of course, linear because we have this time events array. And that's pretty much all the space that we are using here, right? That, and of course, the sort is using whatever space it is going to be using. And so yeah, so that's, just a quick review of this pattern. Now, our live classes, I believe Rohan might have already mentioned this. Our live classes are they go in more depth and they're longer than the the 60 or 90 minutes that we had today. And in that also, it's a similar format where we solve problems, talk about concepts, and of course the whole thing is recorded. The actual classes are all recorded, and you get the recordings. This out here, if people want to take a screenshot, this is some homework problems that you could practice. Again, these are all based on